Hi, everyone. I'm Lily Rapaport. Thank you for joining this session in which we'll be talking about creating a machine learning strategy for product managers. Just a little bit about me. I've been working at Amazon for 3.5 years now, most recently at a new AWS machine learning service for fraud detection. So today we'll cover a range of topics that will help you start building your machine learning strategy. My goal is not to cover these topics in details, but to help you understand what elements you should think about in your product strategy, what trade-offs you might be making, and what additional research you and your team might want to do in the process of creating your strategy. Also, I'll say that I'm talking from my own experience and knowledge, but there are endless resources out there for you to get other perspectives on these topics. And I personally always try to learn new things and expand my knowledge. So the first couple of slides will be at a higher level, and then we'll dive deeper into each topic. So with that, before we start digging deeper, I wanted to cover that cliche basic slide of what is ML, and maybe start by asking, why should you even care about machine learning? Our goal here today is to break that buzzword into practical terms. When applied right, machine learning can truly transform businesses and bring more money and better customer experiences to the table. So there has been many studies to demonstrate the value of machine learning to businesses. As an example, Microsoft found that companies using AI are outperforming by 5% those that have no AI strategy. The basic definition of machine learning is giving systems the ability to act and to iteratively learn and make adjustments without any explicit programming. Machine learning is about looking forward and asking what we can predict about the future and what will happen in various scenarios. So while many machine learning algorithms have been around for a long time, the ability to automatically apply complex mathematical calculations to big data over and over, faster and faster, is a recent development. You probably already know that you're using many machine learning-based products every day already, like the results you're getting in Google search or Amazon, the movie recommendation you get on Netflix, and the fraud alerts you get from your bank on suspicious transactions. And this is only a small fraction of how we'll use ML in the future. And it's really exciting to think about what ML can bring to our everyday lives in other industries like healthcare, manufacturing, self-driving cars, and more. For those of you who are less familiar with practical machine learning, this chart can help you start understanding and visualizing what the process of implementing ML looks like. So we start by defining the problem, just like we would do for any other product. We then collect data, prepare the data for training the model. We'll then train a model, evaluate it to make sure that it's up to par with what we're looking to achieve. We'll then deploy the model in a production environment or in an experiment, or maybe even offline, and we'll then figure out how we want to improve the model. And this is a very iterative process. So while the error is moving in one direction in this chart, it's important to know that this process is very iterative and experimental. The more ambiguous the problem, the more iterations you should expect. And the reason for that is that there's no one way to apply machine learning, and there's no one way to solve a certain problem. In most cases, problems and solutions are very specific to the use case of the company, the data that the company has, and so on. And so every company is willing to make different trade-offs and is looking to optimize different things. At a high level, approaching the product definition, like we just mentioned, of a machine learning application is not different than any other web, mobile device, infrastructure, or any other type of application. So the focus is still going to be solving a specific pain point for a specific use case, and then creating a great user experience, measuring KPIs and business metrics. However, the product that you build using ML will interact with machine learning systems somewhere in your product workflow. And at some point, depending on your use case, your product system will send that data to a machine learning model and will receive a prediction in return and then take an action based on that prediction. It's also important to note that don't let the technicality of machine learning distract you from your big picture vision and goals. The product vision describes the future we're trying to create, typically somewhere between 2 and 5 years out. And so the product vision should act as the North Star for all your product development, including your ML products. So whatever the goal is, your strategy is how you're planning to go about accomplishing that goal. So the concept of be true to your mission, but flexible in your solution applies really nicely in machine learning because of the iterative and experimental nature of it. So the first topic that we'll cover is aligning on the problem. So let's start with that topic. So the first thing you really want to ask yourself is, should I even use machine learning? And the answer is not necessarily yes. So here are a few questions that you can start asking yourself to evaluate if machine learning is the right choice for your product at this time. So number one, is your problem complex enough? A good indication that the answer is yes can be that you have a lot of data points, but no clear understanding on how all those variables act together. You might have changing patterns based on the time of the day or the year, the geography, etc., and you might not understand exactly how to approach these. Ask yourself, is there a simpler solution to your problem? Number two that you can ask yourself to evaluate if machine learning is the right way to go is asking yourself, is your problem big enough? And when I say big here, I mean important. Implementing machine learning is not going to be easy, so you better make sure that the problem that you're trying to solve is worth it. Many companies read about machine learning with enthusiasm and decide to find some way to use it. Don't start with the solution and don't decide that you need to use ML just because. Pick a business goal that actually matters a lot to your business and that seems to have a high likelihood of being solved. And then ask yourself, what mission critical business information are you dying to know but can't currently access? Maybe it's understanding how to yield the highest customer lifetime value or the user behavior most indicative of expected churn. Whatever it is, it needs to be big and it needs to be important. The third question that you can ask yourself is, can your problem be solved with consistent logic? If you're trying to solve a one-off problem, machine learning might not be a good fit. Where machine learning really brings value is in making repeated decisions that are time-consuming otherwise. So can you clearly define the problem and articulate a repetitive approach to solve it? For example, automating a time-consuming task that takes up many people's time every day could be a great use case candidate for machine learning. But building a machine learning model to predict who would be the next pope, probably not so much. The fourth question you should ask yourself is, can your solution afford some error? You should know that every machine learning model will make errors. Can you tolerate that risk? And do you have protections against those errors? The definition of good enough predictions might be set by the regulation, depending on the industry that you're in. So for example, machine learning for making medical diagnosis must be meet government standards. And it can be set by user requirements. So for example, if you're building a chatbot for customer service, it has to be good enough to interact with users so that users don't end up wanting to speak to a human. Or it could also be set up by your competition. So for example, if you're seeking to build a system that recommends songs that users might like, you will probably compete with Spotify machine learning capabilities. So that would be your benchmark. And to make good enough predictions, one of the challenges is the amount of time and effort involved in creating or accessing sufficient training data to build a great model. So that brings us to number 5. Do you have access to that relevant data? So to build a model, you need training data. You need a lot of data. And that data will basically give the machine the ability to learn how to make the right decisions, what the right decisions look like. So it can make those decisions independently going forward. And there are ways to sometimes bypass this challenge. We'll kind of talk about that a little bit later, but for the most part, you need to have enough what we call ground truth data that is labeled examples of what real life and decisions made by humans look like. So again, if we want to align on the problem, there are really 3 ways when we're thinking of machine learning types of use cases, 3 buckets that I would say. The first one is descriptive. So this is the classic data analysis to find patterns. So for example, understanding why sales dropped or what led to a system failure, that's the descriptive bucket. The second one is predictive. So this is the more classic machine learning to make predictions based on input. So for example, predicting a real estate or stock prices or what movie recommendations we should suggest to customers. And the last one is prescriptive. This one is much more rare, and this would be a system that tells me what to do next. It's more open-ended game theory type of a use case, and specifically it's where reinforcement learning comes into the picture. Think getting a machine to play chess or navigate a self-driving car. Most importantly, you should really try and solve a defined specific problem and really focus. Most machine learning applications come down to either predicting a value like a dollar amount or quantity, predicting a classification like predicting if an item belongs into a specific category or not, like spam or not spam. Or third is recognizing and understanding images, language, and sentiment. When you look at these business examples that I have here up on the slide, try to identify what type of machine learning they're applying. So now that we have the problem and we know that it's a good fit for ML, we need to define a goal for our ML-based product, just like we would without using ML. And when we set goals and define the success criteria, we want those to be specific, measurable, attainable, relevant, and time-bound. So this is a really nice research that was published on Harvard Business Review on the benefits of AI, and the benefits on this slide are pretty high-level improvements that machine learning can drive in the business, but I do encourage you to be much more specific about setting business goals. This could be a percentage improvement in the click-through rate, reduce manual effort by a number of hours, etc. The second measurable goal that you should think about is how will you know that the model is good enough of a solution to your problem? And that really comes down to making sure that your model objective is optimizing for the right thing. So in order to find the optimal solution, we need some way of measuring the quality of any solution. And this is done with what is known as the objective function of a model. And the word objective is used in a sense of a goal. The function takes the data and model parameters as arguments, and our goal is to find values for these parameters that will optimize the model for your use case. This is something that you will talk about with your data and research team, but for now, you should know that different models can optimize for different things. For example, minimizing loss to find a really accurate answer, or maximizing likelihood to optimize for profitability or click-through rate. Another important measurable goal to consider in your machine learning application is latency. In other words, how long does it take for your model to run and return a prediction? Machine learning models can be used in real time as data comes in or offline in batch process, and your latency requirement will be highly influential of your system design. And you're almost guaranteed to make trade-offs between your desired latency and accuracy. And it's going to impact some of the decisions that I outlined here in the slide. So moving on to the third step that starts to really get into the strategic implementation. When we talk about the level of abstraction, we mean to ask, do you want to design and build the machine learning process on your own from scratch? Or are you willing to leverage existing solutions that are less customized to your use case? And as we'll see in a bit, building a machine learning solution requires careful thinking and testing and selecting algorithms, selecting data, cleaning the data, testing in live environment, and so on. There's no out-of-the-box machine learning solution for unique and complex business use cases. Even the extreme, most common use cases like recommendation systems and predicting customer churn all those applications will vary widely between customer to customer, between model to model, and will require iterations and adjustments. So if a company goes into a machine learning project without resources committed to an extended period of testing, it might never achieve a useful result. So you have to make sure that you can actually make that investment. Capturing business value for machine learning implies having trained talent in the field of machine learning, from machine learning DevOps, data engineers, machine learning research scientists, product managers, annotators, and so on. So if your company is unable to meet this investment, leveraging a machine learning API with generic solutions or an AutoML service that automates the model building process for you might be a better route. In that case, some of the next steps we'll talk about might already be taken care of for you, like selecting the algorithm or even training the model. On number 4, we have feature selection. So while before we talked about making sure that you have enough training data, here we're trying to really pick and choose which data is actually meaningful to solve your problem and improve the performance of your model. Feature is another word for variable. So here we can see that if you're trying to improve click-through rate of pet food ads, knowing the eye color of the customer is probably not going to help you make better predictions. Just because we have the data doesn't mean that we need to use it, especially as it comes to data privacy, as we'll talk a bit about a little later. So why would you not want to use all the data that you have? Usually there are 4 reasons. The first one is latency. Your model will get too big, and that means it will get too slow. The second one is maintenance. You'll find it too difficult to maintain many data streams that just don't improve your model performance. The third one is data privacy. So you may not want or be able to use sensitive data to comply with data privacy regulations. And the fourth is bias in machine learning. You want to make sure that your model is not biased. For example, in most cases, you wouldn't want to use gender as an input to your model. Eye color, like in this example, can also be proxied to ethnicity. So those should not play a role in most use cases. Number 5, we have algorithm selection. So I won't cover this topic too deeply, but at a high level, I'll go through some of the basic concepts. I highly recommend that when you begin to work towards your ML solution, you read and research about the specific algorithms that your science team is targeting. There are usually many online resources like white papers that are really, really great, even for less technical product managers. So if you're talking about very basic machine learning concepts and making sure that you kind of understand the basics, let's start with model. So what is a model? It's not magic. The model is the artifact that is usually a definition of inputs and outputs, as well as a file that initializes and runs the model. And the model is trained using a machine learning algorithm. So what's an algorithm? An algorithm is a set of inputs and outputs and a set of rules and statistical techniques used to learn patterns from that data. So you can look at the examples in the table. An input could be a voice recording, and the output could be this transcript of that input in an application like speech recognition. And so the algorithm will take that input, transform it into the output using a set of rules. Moving on to supervised learning, which is one of a few key concepts in machine learning. We train a model, in the supervised machine learning, we train a model from input data and its corresponding labels. So supervised machine learning is analogous to a student learning a subject by studying a set of questions and their answers. And then after really mastering those questions and answers, the student can then provide answers to these new, never seen before questions on the same topic. In unsupervised learning, we train a model to find patterns in a data set, typically without labeled data set. So the examples in your data set are not labeled. So in the previous example, you wouldn't have the answers to the questions. The most common use case of unsupervised learning is to cluster data into different groups of similar examples. So clustering can be helpful in areas where it's very hard to achieve true labels, and it's very hard to obtain them and maintain them. So for example, in examples like fraud, clusters can help humans better understand the data without needing to label every single example, whether it's fraud or not fraud. And semi-supervised learning is basically a mashup of the two. So we train a model on data where some of the training examples have labels, but others don't. One technique is to infer labels for the unlabeled examples and then trained on the inferred labels to create a new model. Reinforcement learning solves a specific problem where the decision-making is sequential. So each action brings a reward and moves the acting agent to another state of the environment. The goal is for the agent that is acting on those policies to optimize a long-term reward. So use cases can include gaming, robotics, navigation, inventory and supply chain management, and financial trading strategy. And then finally, deep learning. So deep learning is a type of neural network containing multiple hidden layers. So this is where a lot of the innovation is really around these days in the areas of neural networks. It combines sophisticated techniques like computer vision, natural language processing into layers of deeper learning. So that means there's more than one layer to how the algorithm works. And it's mostly used in areas like image and text recognition. It's really great for complex modeling, but it could definitely be an overkill for a simpler, everyday business use case that can honestly rely on established machine learning frameworks and techniques with far less parameters. On number 6, we have evaluating your model performance. So the success of your machine learning product ultimately depends on how good your model predictions are. You may encounter a lot of different ways to measure and evaluate the model performance: precision, recall, accuracy, odds ratio, area under the curve, and so on. All these are measures for model quality. This is not the place to describe them all in a lot of details, but just be aware that these different measures are associated with different trade-offs that you as a product manager will need to make. So for example, reducing your false positives, like transactions that you wrongly marked as fraud, is likely to result in an increase to your false negatives, which is the number of transactions that you wrongly deem legitimate. And then finally, we have productionization. So basically putting your machine learning models in production. When the model's performance is satisfactory, we need to establish whether it can actually be deployed in production, or in other words, can it be used in production, in a production system, so that the predictions that it makes are actionable. Before you productionize a model, you'll probably want to learn do some experiments. You might even have 2 models being used at the same time, one champion model and a challenger model, where you're trying to really use a challenger model to test new features that you want to experiment with. And once the successful pilots are identified, the next logical step is to deploy them in customer-facing business strategies and operations. To continue with our fraud detection example, a deployed model will help us evaluate the risk of transactions in real time. So we need to be able to collect and store and score data continuously in order for a model to make predictions that are available quickly in order for them to be actionable. So that means we need to construct a really, really robust data pipeline to support near real-time data acquisition and scoring, which is why good data engineering is such a necessary and important step in the machine learning pipeline. Your machine learning pipeline is basically the infrastructure surrounding the machine learning model and algorithm. It includes gathering the data from the front end, putting it into training data files, training one or more models, and exporting the models to production. So the last part of this presentation is really things that you should worry about. So when you choose to implement machine learning in your product, there are some things that you need to think about in advance. The first one is data preparation. You need to make sure that you can access data and scale. You need to think about imbalanced data, about outliers in your data, missing values, label definitions, having too much data and having too little data are all things that we touched on. The next thing is architecture selection. So using inappropriate technology infrastructure, bad software engineering practices, lack of model governance can all take a great model and really turn it into something that cannot be used. So you really want to make sure that the orchestration around different operating systems really maintain the highest standards that can really bring your model to life and bring value to your business. Parameter selection is something that we roughly touched on, but what you need to know is that for each learning, selecting the right values for each hyperparameter is really important. Some examples of it could be learning rate, regularization, number of layers, and so on. Just make sure that you're aware of these things. Retraining strategy is another challenge that we need to basically periodically update the training data. It's not always an issue. It won't apply in basic contexts in which the prediction was made stays constant, the environment stays constant. So in these constant environments, after a certain point, the value of bringing additional examples into the training database is almost zero. But in other cases, algorithms need to be frequently updated with completely new data, reflecting changes in the underlying environment. So, for example, navigation apps, right, like Google Maps, you could think of new roads, traffic circle, different street names, similar changes that really need to be updated as those changes happen in real life, so that the predictions become or stays accurate over time. The next one is data privacy, which we also touched on. So this is a really, really key point and something that you as a product manager really need to be mindful of. So data privacy protection concerns are driving a lot of regulations around the world to improve personal data protection. Two really prominent examples are the California Consumer Protection Act that protects data privacy and helps individuals understand what data is being collected and how it is sold or disclosed. The second one is the General Data Protection Regulation, or the GDPR, which was created to protect the privacy of individuals in the European Union. So in machine learning, this means that you need to be very intentional and careful about what sensitive data you collect, how you process it, how you store it, and how you train your model to make predictions based on that data. The next one is bias and fairness. So first, models may have hidden biases derived from data provided to train the system. So for example, if a system learns which job applicants to accept for an interview by using a data set of decisions made by human recruiters in the past, it may learn to perpetuate their racial, gender, ethnic, or other biases. So these biases may not appear as an explicit rule in the model, but it's embedded in the subtle interactions among the different variables that are considered in the model. The second point here is that when machine learning model does make errors, and it probably will at some point, diagnosing and correcting exactly what's going wrong can be really difficult. So the underlying structure that led to the solution can be very complex, which brings us to the next point of machine learning explainability. So depending on your use case, you may need to explain how you got to a certain prediction. Depending on the industry, you might need to do that for regulatory reasons. But depending on your model, it might be more or less difficult to do that. So machine learning models are usually a black box, especially if we're talking about deep learning models, unless you implement specific features to compute the explanation for how the model was built and how it arrived at making specific predictions. And then the last and final point here is cost control. So it's important to know that both model accuracy and model inaccuracy cost money. Both false positives and false negatives incur cost. And so we have to be very clear what is the acceptable tolerance for these kinds of errors. When reviewing the business case for deploying a new model, just ensure that these costs have been properly accounted for. That's all I have for today. Thank you for joining. Please feel free to reach out to me if you have any questions or feedback. And thank you for listening.